Hello. So in this lecture, let's continue right at the moment where we left the discussion over from last time and go a little bit into more details on how to establish these Legendre series, which will be used in eventually solving boundary value problems in spherical coordinates. So from last time, we proved that the Legendre polynomials are orthogonal on the interval -1, 1. Okay, so you don't have to write it down because you should have it on the notes already. But what that means is that if you take the product of any two polynomials and integrate them in the interval -1, 1, the integral is 0 if m is not equal to n, so for any two distinct polynomials. And if m is equal to n, the integral is 2 over 2n plus 1. So this allows you, the orthogonality allows you to come up with a series in terms of these polynomials, the so-called Legendre series. And notice that in this case, this formula for the orthogonality gives you the formula for the coefficients of the Legendre series. So basically, if the function is piecewise smooth, on the interval -1 and 1, then you can write the function as a series in terms of these polynomials where the coefficients are given by this integral. So here I meant, f of x, not x. I mean, x would be one of our examples, but f of x times Pn of x dx with 2n plus 1 over 2 in the front of it. So when you solve for the coefficient. So we did this last time. But you will see that for some boundary value problems, you will have to use different intervals like 0, 1. For example, if you take a hemisphere, remember -1, 1 comes from theta, that angle from spherical coordinates between 0 and pi. So one remark I made at the end of a previous lecture is that if you look at just the even polynomials, even Legendre polynomials separately from the odd ones, these are also orthogonal on the interval -1 and 1, but also 0, 1, because it's not necessary to take in that case the full interval -1 and 1, because the even polynomials are even functions and the odd polynomials are odd functions, but the product of any two of them will be an even function. So one remark before we move on with our discussion here. This is a result known from calculus basically. If you have an even function, suppose you have an even function h of x on some symmetric interval -a and a, then the integral from -a to a of that function is equal to twice the integral from 0 to a of the same function. I don't remember if I mentioned this last time, but if you look at the graph of an even function, that's obvious, right? I mean, why that's the case? Because the function is symmetric with respect to the y-axis. So the integral from -a to a is basically twice the area, right? I mean, twice the area between 0 and a. So this is actually the result that gives me a quick way to show that the polynomials, the even and the odd polynomials taken separately, are also orthogonal, in particular on the interval 0, 1. So I can actually rewrite this integral here, and I can say that the integral from 0 to a of that function, again, if it's even, is 1/2 the integral from -a to a of the same function. So remember, it's customary to write the even polynomials as p2n of x, the even Legendre polynomials, for convenience. So basically, n still goes from 0, 1, 2, 3, and so on. But because the index is 2n, you're basically looking at just the even coefficients. 2 times 0, 2 times 1, 4, 6, and so on. And the same thing if I took separately the odd polynomials, p2n plus 1 of x, and again n from 0, 1, 2, 3. This will produce basically the odd polynomials, the Legendre polynomials with odd degree. And again, because the product of two even ones and the product of two odd ones always give me an even function, I can basically rewrite this this integral in terms of the interval from 0 to 1 when I take the evens and the odd ones separately. So let me illustrate what I'm talking about here. So suppose I look at the integral from 0 to 1 of p to n of x, p to m of x. So I'm basically checking the orthogonality for the even polynomials separately from the odd ones. Now, because this is an even function, this is based on the remark I just mentioned here. This is basically 1/2 the integral from -1 to 1, p to n of x, p to m of x dx. And we can basically use exactly this formula by replacing n with 2n and m with 2m. So these are still orthogonal on the interval -1 and 1. This equality shows that basically the even ones are also orthogonal on the interval 0, 1. So it's not necessary to take the full interval -1 and 1. And the answer for the integral, of course, is again 0 if m is not equal to n. And pay attention here, if m is equal to n, I'm going to copy the same thing here, but I'm going to replace n with 2n. Yeah, because that's my notation for the index now. So this is going to be 2 over 2 times 2n plus 1, which makes it 2 over 4n plus 1 if m is equal to n. So what does that accomplish? And I forgot the 1/2, I'm sorry. So there's a 1/2 out of it, right? So it's times 1/2 to cancel. So it's really 1 over 4n plus 1. What does that accomplish is that not only we show that the even polynomials are orthogonal on the interval 0, 1, but also we can have an even Legendre series. Basically, a series involving just the even polynomials. So in other words, you can write a function as a naught p naught of x, a2, p2 of x, dot, 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 just involving the even coefficients. In which the formula for the coefficients a to n kind of follows the same formula from here, but basically using this coefficient. So when we solve for the Legendre coefficient, when you take the reciprocal of this, instead of 2n plus 1 over 2, is going to be 4n plus 1 over 1. So a to n will be 4n plus 1, the integral from 0 to 1 f of x p to n of x dx. Again, this is a kind of finding the cosine series, basically. You include basically the even functions. It's somewhat analogous to that process. And by the same token, if we do, let's do it on a different page. If we look at the odd coefficients, odd polynomials together, again on the interval 0, 1. So let's say I'm looking at the integral of p to n plus 1 of x, p to m plus 1 of x dx. Again, because the product of two even functions is also, of two odd functions is also even, this will be the 1/2, the integral from -1 to 1, p to n plus 1 of x, p to m plus 1 of x. And again, from the previous results, we know that this is 0 if m is not equal to n. And if m is equal to n, again, I'm going to plug in now 2n plus 1 instead of n. So instead of 2 over 2n plus 1, I'm going to replace n with 2n plus 1, which is the answer if m is equal to n. And again, I forgot that 1/2, right? So 1/2 in front of it. So notice if I actually cancel this 1/2, then the answer is going to be 0 if m is not equal to n. And simplify this one becomes 1 over 4n plus 3 if m is equal to n. And so that basically leads to the so-called odd Legendre series. Because again, now I can write that same function as a1 P1 of x, A3, P3 of x, dot, 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 A2n plus 1, P2n plus 1 of x, and so on, in which A2n plus 1, just like before, now it's given by the reciprocal of this when you compute the Legendre coefficient, 4n plus 3, the integral from 0 to 1 f of x, P2n plus 1 of x dx. So you should have it in, you should look at it in the formula sheet. I don't think you should write it down, maybe again on your notes, because again, that handouts has all of this in a more compact form. But basically, with the orthogonality, we arrive to 3 types of Legendre series, which will pop up depending on the type of boundary conditions you will have. So either you have the function as a full series of all Legendre polynomials on the interval -1 and 1, and in that case, an is given by 2n plus 1 over 2 integral from -1 to 1 f of x pn of x dx. Or depending on some boundary conditions, as we mentioned already, you may have to take into account only the even polynomials, in which case the typical index will be denoted by 2n, and the interval should be 0, 1. It's the same on -1 and 1 because of the symmetry, remember. And the formula for the coefficient for a2n will be 4n plus 1, the interval from 0 to 1 f of x p2n of x. And then finally, you could have a representation in terms of odd Legendre polynomials on the interval 0, 1, in which case the coefficient will be given by 4n plus 3, the interval from 0 to 1, f of x p2n plus 1 of x dx. So this is again analogous to sine series, cosine series, the overall sine Fourier series involving both of them. I mean, to an extent, of course, I mean, these are polynomials and not sine and cosine. Let's finish this part. Well, yeah, we're going to finish this part for now. We're going to continue with the second part with a couple of examples in terms of how we can compute this Legendre series. Obviously, you could use tables of formulas, but if you have to use your own work, I mean, if you have to come up yourself with these integrals, there are a couple of relations you can use to make your job easier. And just like the Bessel functions, we're going to limit ourselves to do by hand only the case in which f of x is a power of x, x squared, maybe x to the power of 3, but you will see it gets quickly, sorry about that, quickly complicated. So we're going to continue with the second part. Phone rings.